Hey, welcome to Electro-Knowledge. Today, we are going to tackle one of the most powerful secret weapons in all of circuit analysis, Thevenin's theorem. If you've ever felt totally lost looking at a complex schematic, stick around because this is going to change how you see circuits forever.
You know the feeling, right? You're staring at a circuit diagram that looks like a tangled mess of wires and resistors, and all you need to find is the current through one little part. It feels like you have to solve the whole giant puzzle just for that one tiny piece. Well, what if I told you there's a much, much smarter way? And this is it. This is the magic right here. The Thevenin's theorem tells us that any linear circuit, no matter how big and scary it looks, can be swapped out for this incredibly simple equivalent. Just one single voltage source, which we call Thevenin, in series with one single resistor, Thevenin. That's it. All that complexity just boiled down to two simple components. The best way to think about this is the black box idea. The theorem lets us take that whole messy network of components and basically stuff it inside a box. From the outside, where we want to connect our components, that entire box behaves exactly the same as our simple little two-part circuit. We don't have to care what's going on inside the box anymore. We only need to know its effect right at the terminals. Okay, so that's the theory, and it sounds pretty cool. But why is it considered an absolute lifesaver by engineers? What makes this so useful out in the real world? Let's dive into why this is a must-know tool. The number one reason, it's all about saving time and effort. Imagine you're trying to figure out the perfect load resistor for your circuit. Without Thevenin's, you'd have to do all the complicated math over and over again for every single resistor you wanted to try. But with Thevenin's, you do the hard work just once to find that simple equivalent circuit. After that, testing a new load is just a quick Ohm's law calculation. This saves a massive amount of time, and that's why it's used in everything from designing power grids to building the charger for your phone. And here's the best part. Applying this isn't some kind of abstract art form. It's a straightforward, repeatable recipe. Let's walk through the 5 simple steps you can follow to find the Thevenin equivalent of any circuit. Here they are, the 5 key steps. First, you identify the load. That's the one component you actually care about, and you just temporarily remove it from the circuit. This leaves you with 2 open connection points. Second, you find VTH by calculating the voltage across those 2 open points. Steps 3 and 4 are all about finding RTH. You turn off all the power sources in the circuit and then calculate the total resistance you'd see looking back into those open terminals. And finally, step 5, you draw your brand new, super simple circuit and pop your load resistor back in to get your answer. Now that step about deactivating sources is absolutely critical, so let's zoom in on that for a second. What does that actually mean? Well, for an ideal voltage source, making its voltage 0 is the same as replacing it with a perfect wire, a short circuit. And for an ideal current source, making its current 0 is like cutting the wire completely, an open circuit. You have to get this part right or your Thevenin will be way off. All right, enough theory. Let's get our hands dirty and see how this works in practice. We're going to take a circuit that looks kind of tricky and use our 5-step recipe to simplify it right now. So here's our circuit for today. It's got 2 voltage sources, a 28-volt and a 7-volt, and a few resistors hanging around. Our only goal here is to find the current flowing through that 2-ohm resistor, which we'll call our load. Now, we could use something like mesh analysis to solve this, but let's see just how much easier Thevenin makes it. Okay, first things first. Step 1. We identify our load, the 2-ohm resistor, and we just lift it right out of the circuit. This leaves us with 2 open terminals. Everything we do from here on out is to figure out what the rest of that circuit looks like from the perspective of these 2 points. Step 2. Let's find VTH, the Thevenin voltage. This is simply the voltage across those 2 open terminals we just made. And notice what happens. The moment we took that load resistor out, the rest of the circuit became a simple, single series loop. Since no current can flow out of those open ends, the problem just got a whole lot easier to handle. Let's run the numbers. The 2 voltage sources are opposing each other, so the net voltage driving current around that loop is 28 minus 7, which is 21 volts. The total resistance in the loop is just 4 ohms plus 1 ohm, which is 5 ohms. So, using our good friend Ohm's law, the loop current is 21 volts divided by 5 ohms, which gives us 4.2 amps. Now, to find the voltage at our terminals, we can start at the 28-volt source and subtract the voltage drop across the 4-ohm resistor. So, 28 volts minus 4.2 amps times 4 ohms gives us our VTH of 11.2 volts. And there it is, 11.2 volts, that's our VTH. The first half of the puzzle is solved. Now we just need to find the resistance. All right, on to steps 3 and 4. Find the Thevenin resistance, RTH. For this, we go back to our circuit without the load and we deactivate those sources. Since they're both voltage sources, we replace them with short circuits, just wires. Now, look at the circuit from the perspective of our open terminals. You can see that the 4 ohm and 1 ohm resistors are now connected in parallel. And the calculation for 2 resistors in parallel is super easy, right? It's just their product over their sum. So that's 4 times 1 on top divided by 4 plus 1 on the bottom. That's 4 divided by 5, which means our Thevenin resistance is 0.8 ohms. That's the total equivalent resistance that our load resistor is going to see. And we did it. We've got our Thevenin and our Thevenin. That means we can now take that entire, original, complicated circuit and just replace it with this beautiful, clean, simple equivalent. A single 11.2 volt source in series with a 0.8 ohm resistor. Look how much easier that is to work with. And now for the final payoff. We take our original 2 ohm load resistor, the one we set aside at the beginning, and we connect it back to our brand new equivalent circuit. And just like that, a problem that looked pretty messy is now a basic high school level series circuit that we can solve in our heads. The total resistance in our new circuit is just RATH plus our load, so 0.8 plus 2, which is 2.8 ohms. The current flowing through that load is the total voltage, 11.2 volts, divided by that total resistance, 2.8 ohms. And that gives us a final clean answer of exactly 4.0 amps. Simple, powerful, and so much faster. So let's just do a quick recap. What are the key ideas that you should pack into your personal Thevenin toolkit from now on? Just remember these 3 things. The Thevenin voltage, VTH, is the voltage you find across the open terminals where your load used to be. Thevenin resistance, RTH, is the resistance you see looking back into those terminals when all the sources are turned off. And those two together create your equivalent circuit, which behaves exactly like the original messy one. And this really gets to the heart of it all. The Thevenin's theorem isn't just some neat calculation trick. It's a really powerful way of thinking. It's like a bridge that lets us take all the messy, real-world complexity of a circuit and connect it back to the simple, elegant, fundamental laws of physics. Thanks for hanging out with me here on Electro Knowledge. If this helped you finally understand Thevenin's theorem, please do me a favor and hit that like button, subscribe to the channel, and maybe share this with your fellow students. We'll see you in the next one.
Thanks for watching. Like, share, and subscribe to Electro Knowledge for more electrical concepts.